when we are in a two-dimension, how do we compute the position, velocity and acceleration vectors? And what is projectile motion and relative velocity? Very simple, actually. You know almost everything from chapter 2. Take a look. This is a position to point P. We have a vector position R, which has a component Y and a component X. Well, you know what to do because you already used this one quite a lot in chapter 2. X component square plus Y component square under the square root. How about the velocity? Again, you know also this one. This is the trajectory. If you take the average delta R between point 1 and point 2, the change in your velocity, therefore the average velocity, will be the change in your displacement over time. How about instantaneous? Instantaneous, I want you to remember that the velocity will be tangent. Exactly right there. So this is your trajectory, and here we have a tangent velocity. So I'm gonna do the X component and the Y component. So these two are the same, right? In this case, we want the interval of time to become very, very small, down to 0, down to a milli or a micron second or a picosecond of delta R over delta T. The acceleration in 2D, right, in 2 dimension, very easy, because again, if your velocity is a tangent to the trajectory, you see velocity tangent, your acceleration will always point toward the concave side of a curved path. Right? When you are driving on the freeway, on a ramp, and you feel like, a leaning, that your acceleration point toward the concave or pointing toward an imaginary center, right? If you could extend this acceleration, here you will find the center C of your curved path. So this instantaneous acceleration, it's very easy to find, is the limit, and the average acceleration is always a change in velocity over time. Yes, when we drive, when we change our velocity over time, we accelerate. So take a look, because now the acceleration will have also 2 components. And I like this slide a lot. This is actually more simple. In blue is the parabolic path, in green your tangential velocity. Take a look, this is the A, your acceleration pointing toward the center C with component A of X and A of Y. Look, the angle is always counterclockwise from the x-axis, right? This is also the component A of Y. So how do you find the magnitude of this acceleration? Very easy, you know it. And if I ask you what is the direction of A, of your acceleration, is the inverse of the tangent, vertical A of Y over A of X. That's theta, your direction. Truly spectacular. Theta computed counterclockwise from the x-axis. We get to the projectile motion. Yes, you use it all the time. You play football, baseball, soccer, any sports. It's in our everyday life. Now, initial velocity, gravity, and air resistance, this thick gelatin, are important for projectile. So take a look, this is a simple step, right? It's a nice parabolic trajectory. At the very, very beginning, there is this initial velocity, right there, initial velocity that is tangent to the trajectory. Now this object is moving up to a max and falling down, and it falls down under an acceleration of the gravitational field of this planet. You already know it is A of y minus g, y minus, because it's a down where? Toward the center of this planet, and is the famous value minus 9.8. Is there an A of x component for this acceleration? Yes or no? Well, let me ask you, an object that is falling, is there an horizontal acceleration, is moving horizontally? The answer is no, is 0. Why? Because look, I'm gonna have this object, right? This object, when I let it go, it only falls under A of y. I could have a of x, an horizontal acceleration that moves the object accelerating along the x-axis. But the only way I could have a of x is to attach an engine with propulsion that push it toward the x-axis. But this is a sci-fi, and why we want to do it? Why we want to give this object that is falling an horizontal acceleration? So projectile, because of this condition, it's very simple and easy, good for you. Now I'm gonna zoom into that initial velocity, right there, right at the center of the origin, right there, that's your initial tangent. Look, I'm gonna zoom into, because I want you to see that this initial velocity, that's the corresponding angle measured counterclockwise from the x-axis, has components. Yes, we love components. So v of x initial, wants the cosine because it is adjacent to angle theta, and this one, I'm gonna put it in red, is a v initial on the vertical axis, which wants the sine. So make a note, very, very important. So important that I even summarize for you. This is just for this initial velocity. This is a main character. This is a star. A main famous initial velocity. Components, right? The initial speed, magnitude, and the angle, you know how you kick the ball, the direction, right? Direction, angle, theta, you already know. Vertical component over horizontal. Again, super important, make sure you have it on your summary. I love this photo, oh my goodness. Look at that. You already know about G, that is your vertical acceleration. I'm going to add that there is no component horizontal, right? No horizontal component. You remember, unless I attach a propulsion engine, but why do I want to do that, right? So that's all you need to know right here. I'm gonna put it in a heart shape because I want you to love it. There is only a vertical component for the acceleration, your negative g. Stay with me. You remember this star important character, the initial velocity. Here's the initial velocity, which has an initial component on the x-axis. V0x. Aha. Take a look. This one is the same, is the same, is the same, and it will be the same even here. Doesn't change. The horizontal component of your initial velocity do not change. Look horizontally. The projectile exhibit constant motion. Yes, this is the same. V0x, V initial, they are all the same. Truly spectacular. So what's gonna change? What's gonna change, is the vertical component of your initial velocity. Take a look, I'm gonna do it in blue. This is the maximum initial component of your velocity, right? Then it becomes a little bit less, down to 0. Wow, V at the top is 0. Of course is 0, because this initial velocity at the maximum has only an x component that is the parallel to the x-axis, right? Then what's interesting, if this is pointing up, this initial velocity now points down. You remember why? Because when you reach the maximum, you have to stop, right? V0y equals 0 to revert the motion to fall down. So that's why it goes from being up to being down once you reach the maximum, the top. Interesting, right? Spectacular. Please make a note. I know what you're thinking. What did I do? Do you remember this equation? Let's hide my face. Do you remember this equation? Chapter 2, I took a screenshot of the video. I have it online for you. Well, nothing changed, because we are gonna rewrite all this equation right here. The only things is gonna change is that in A of y, we are gonna plug in a minus g. A of y minus g, A of x, 0, because we want to quantify a projectile motion. So again, those equations are exactly this equation. You can even avoid to write them down, but it's better to have them. So this is a y direction motion formula for projectile motion. These are x direction motion for projectile. Remember again, A of x equal 0. So again, we are using a lot of your knowledge. I like this photo. Look, you notice that there is a yellow and a red object falling under free fall. Look, they space out exactly as the same vertical motion. So falling vertically is exactly spaced out as the projectile motion. That's why we are using a lot of knowledge for the chapter 2, because it's a motion along a straight line. And this is a motion in 2 dimensions, the one we are gonna do. That's why it's really easy. Last slide, a new concept. UCM stands for Uniform Circular Motion, which you already saw it. So do you remember that I mentioned to you there is a car speeding along the ramp of a freeway? You have an acceleration pointing toward the center, which has a component right here, a parallel to v, to the velocity, and this one is a perpendicular, a parallel and a perpendicular. Means 90 degree, it makes a 90 degree with the velocity v in green. You see 90 degree there, from here to here. So this acceleration pointing toward the center has two names. Center seeking, centripetal, or also along the radius. Very important equation. Again, if this is a circumference, this is the center, this is A of C, center seeking, and since this is also the radius R, definitely they are exactly the same. Radial acceleration is centripetal acceleration, so you can call it the way you want. I like this one detail. Why? Because now you're slowing down along a circular motion. So take a look, your centripetal acceleration, but look at the parallel component of your acceleration parallel to the velocity is opposite. V points one way and A parallel points opposite. And the last detail, in case you are moving with a constant speed, there is only an acceleration that is perpendicular. So is that to the center of the circle, so is only the centripetal, also called radial acceleration. A physics book slides off horizontally from a tabletop. So if this is a table, this physics book slides off horizontally. You see how important is this word. It has this initial horizontal along the x-axis speed of 110 meter per second. It strikes the floor right there, so this is the floor, in a time of 0,350 seconds. We ignore a resistance. In part A, we want to find age, the height of the tabletop. So this is age, which I'm going to call also as a delta y. So what we know that the book initially moves along the x-axis, it says it is horizontal. Right there, horizontal, only horizontal. Therefore, the initial component on the vertical axis y is 0. Remember, in a projectile, we can treat the x-axis and y independently. Since it's only horizontal, there is nothing going vertically. What else we know from the theory of the projectile is that there is no horizontal acceleration, and the vertical acceleration is always minus g or minus 980 meter over second square. This is a theory always to keep in mind. From chapter 2, but also we saw it in chapter 3, we know this equation that will give us the vertical displacement or the height of the tabletop in this case. This is initial velocity along the vertical axis, time, and this is a of y times square. Great equation. I want you to frame it and keep it on the summary. The great thing is that with this condition, since there is no vertical initial velocity, that goes to 0. The equation, therefore, becomes very simple. Or, I'm going to continue right here. This is a delta y is going to be equal 1/2 ay t squared. Let's plug in with the sign 980 and the time, don't forget to square it. So the final answer will be the value in absolute. So your final answer is absolute value, means without the sign, because this is just the height of this tabletop, how tall it is. With the minus will be a displacement pointing downward. In part B, it says that we want to find the horizontal distance from the edge of the table where the book strikes the floor. So the horizontal will be from here to here. Since it is an horizontal displacement or distance, in this case is a distance, this is what I want to find. In part B, delta x, your distance, is what we are looking for. You remember from chapter 2 and also chapter 3, this is a very famous equation. I also use it above, but this is written for the x-axis. Do you see? All x-axis in this equation. Well, I know that I have everything I need. So delta x will be initial velocity on the x-axis. I'm going to put a heart symbol right there. The time plus 1/2. Here I have an horizontal acceleration, which I'm going to show you here where I put this dot. How much it is 0. So it doesn't matter, we just cross it out. So the final answer, super easy to compute. The book strikes the floor at 0.385 meter. Final answer. In part C, we want to find the horizontal component, vertical component of the book velocity, magnitude and direction just before it reaches the floor. What does it mean? Right here, before it reaches the floor, we want to find v of x, horizontal, v of y, vertical. The magnitude, you know how to do it, the direction, theta. So right here, this is what we want to find, v of x, v of y, magnitude, and direction. Let's do it. Let me draw it again. Tabletop, horizontal, strikes the floor just before we want to find a v of x and v of y. Yes, also the magnitude, but that's easy, and the direction. So from the theory of projectile motion, if you look back on my video, you will see that the initial component on the x-axis for a projectile motion is also equal to the final component. So v of x, it's very easy to find because is that heart value right there. I'm going to say equal that heart value that was of, frame it. For v of y, the final velocity of the book just before it strikes the floor, we need to use the very famous equation from chapter 2. At the same time, this is also very, very easy, because when you look up here, I'm going to say the half moon value, the initial vertical velocity is 0. So again, another simplification, symbol half moon, this is 0. So I can just plug in straightforward this value. I'm going to do in terms of absolute value, or I could also plug in the negative for the acceleration 980 a of y, multiply the time. What you obtain is a value of minus 343 meter over second. The minus will tell you that this vertical component is down, but I'm just gonna frame the absolute value. Absolute means without the direction information, the negative sign. So this is the absolute value for your vertical velocity of the book right there before it strikes the floor. In terms of magnitude, it's very easy, because you remember the magnitude is the square root I have both value. I'm just gonna plug in. This is the heart value, famous one given by the book initially, plus this one. And this magnitude of your velocity will be of 360. Frame it. What is the direction? The direction is the inverse of the tangent. In this case, I'm going to say absolute value of a vertical component over absolute value of the horizontal component. So let's plug in. The vertical is and this one is 110 without the parentheses. Straight. So the final answer will come up an angle of 72.72. Now this angle is computed below the horizontal x-axis. So again, let's visualize what we have. Table, physics book, only horizontal component of the initial velocity, then under gravity it falls down. Right here you will have a negative pointing down v of y is negative, which value is 343. Right here you will have an horizontal velocity of 110. Yes, the one with hard. So your resultant, your final velocity parallelogram will be this one, which value we computed to be via Pythagoras right here. And this angle, the one I'm going to put in blue, will be 72.2 below the horizontal, right there, like that. So in the end, again, this is a great physics problem. There is only an horizontal component of the initial velocity, so there is a vertical component that is 0. This is all theory, the one I put in frame in red, that is all theory. Remember, physics is like going to the gym. Physics equal gym. Repetition, repetition, repetition. If you repeat this problem 2 or 3 times, you will sing it. We want to find her minimum speed so that when she dives off, she's safe and can reach the water. Take a look, this cliff is 9 meters from here to here, and the ledge is 1.75 meters. So what must be her speed just before leave the cliff? So as you can see, V0, this one is what we want to find. Do you notice immediately that it's only horizontal along the x-axis, right? So immediately we have to specify that what we want to find is this one. Since it's only horizontal, we know that her vertical initial velocity is 0, right? Otherwise, instead of going parallel to the water, it will go a little bit high. But she's running off the cliff, so it's only horizontal. Remember, this is a projectile, so the horizontal component of acceleration is 0. The vertical component of the vertical acceleration, or g, is 980 meters over second square theory. Now, for this example, since I don't want to carry all those signs, I'm going to change the Cartesian axis. So I'm going to decide to take the Cartesian axis pointing down, positive y. Now I place it down. So in this case, as you can see, g, or a of y, will be taken as a positive 980 meter per second square. So because this is positive, this one points down, exactly down where I took the Cartesian axis pointing down. By doing this convention, I avoid to carry with me a lot of negative sign, because you see this one applies when the vertical Cartesian axis is a positive pointing up to the sky. Then you have g, gravity, right, a of y, pointing down. Since you see they are opposite, up and down, we need to carry the minus to remind us that is always downward. But when I flip the Cartesian axis, I make it a little bit simpler. So we need to know, we need to find this initial velocity as she dives off. Remember, this initial along the x-axis will be linked to the delta x, will be linked to time, so we need to find a lot of parameters. All right? To begin with, we need to find time. The time she will take to dive to the water. So she's here, jumps down. I want to find the time needed to reach the water. You remember the equation? Now, in this equation, we do know quite a lot because the delta y is a 9 meter. Your initial velocity on the vertical axis is 0. And we have this acceleration very famous. So we can solve it for time. Since this term goes down to 0, do you agree with me that the equation becomes easier? So this is equivalent to say delta y equal, I'm going to solve it for the time. Okay, so I'm going to do times square. Delta y stays there. The 2 goes next to delta y, and the acceleration goes at denominator. Let me write it down more elegantly as the square root of 2 . So I'm going to plug in all the value I have. I'm in great shape. Delta y was 9 meter. And my acceleration, because of the condition I did, is a positive. So it's a positive 980. Why? Because again I flipped the Cartesian axis. So the final time in which she reached the water is 1.36 seconds. Well, this is not the final answer, because remember, I want to find the initial velocity, how safe it is, which is linked to delta x. Do you remember this equation? Well, we have been using it quite a lot, right? Let me ask you, do I have this delta x here? Yes, right there. This is your delta x. Do I have this initial? No, is the one I want to find. But look how elegant is physics. How much is a of x? Well, how about if we look back and we see that that value is 0? We already commented why. So this is a super easy equation. All of that goes down to 0. And I have all right, so this is a delta x. I'm going to solve it for her initial speed along the x-axis. The delta x is the horizontal cliff, right? The 175 meter, and the time in second hasn't changed. So her final speed, her initial speed for safely land on the water has to be horizontal, and the value has to be 1.29 meter per second. A tennis ball roll off the edge of a tabletop. So this is the tabletop. And the height of this tabletop, the delta y, also called the edge height, it's 0.550 meter. Now, if this is the object and is rolling off right there, as it says, it means that this motion is only horizontally, right? So there is no vertical component. So the speed of this ball will have only an component x. As for the component y, since is on a flat plane, is 0, non-existent. So very important information that we derived from the fact that it rolls off on a table. Then it falls off and it will strike the floor. This is a delta x, right, horizontal, at 140 meters from the table. We want to find in A the time in air, time of fall, time of flight. We know already a lot of information because you remember it's a projectile, there is no component x of the acceleration, and the y component is always a negative g, which is a minus 980 meter per second square. Now, what I want to do is actually to flip the Cartesian axis. So here the Cartesian axis was pointing up. Objects are falling down, that's why it's a negative g. The flip I want to do is like this one. You see, I'm going to flip the y-axis pointing down. In this way, this object that falls down is going to fall down under plus g. So with this convention is kind of easier, so I don't have to carry with me those negative sign. We want to compute the time. We know that the ball roll off and then will strike. So what is this vertical displacement? Well, I do know because from chapter 2 we used this formula very, very often. Now, if you analyze this equation, you already see that because of that condition, we can say goodbye. So the equation will be very simple. Remember, we want to solve this equation for the time. So here's a little bit of algebra initially. Now the 2 will go next to the delta y, the acceleration will go at denominator, and now I'm going to make it a little bit more elegant. It will be the square root of twice delta y over a of y. Let's plug in, because the delta y, I have it right there. Right there, where there is this dot. And the a of y, I know is a positive because of this convention. I'm going to put in a positive. You see, big positive, right? 980 meter per second. So if you do the algebra, the time of flight, frame it. In part B, we want to find the magnitude of the initial velocity of the ball. So again, this is an object that is rolling we want to find this component. That's initial, you see, initial we not on the x-axis. I know that the initial on the y-axis is 0 because it's just on the horizontal table. So let's go and compute this initial speed of this rolling tennis ball. Is rolling on the horizontal axis, on the x-axis, so my focus goes to the delta x. So I know this displacement, I know this equation, you remember, we used it before, above. With this equation, we need to analyze and see what we have. First, from the theory, a of x is 0. This is 0, we can say goodbye. Delta x, I know, because is this little value right there. And the time I have, I just found it. So let's clean it up. I'm gonna speed up a little bit. So the time will be delta x, we need to find the initial velocity, will be delta x over t. Delta x, I have it, is that little horizontal segment, 140 meter, and the time I just computed. Velocity is indeed measured in meter per second, so this is the final answer for part B, frame it. In part C, we want to find the magnitude and direction of the velocity of the ball before it strikes the floor. Okay, let's do it. So in part C, again, this is the table. It rolls, it falls. Right here, we want to find the final velocity on the x component. We want to find the final velocity. Then we are going to compute the magnitude, right, the square root, and then the direction, the inverse of the tangent, which is theta. The good advance we have is that since it's a projectile, the initial velocity on the x-axis, it's equal to the final on the x. So that is done. I already know the value is from part B, frame it. Do I know V of y? Well, while V of x, the final, was easy to find, V of y requires to remember that it depends on the initial velocity plus AYT. So we need to use this equation. Now you remember my comment that there is no vertical component, so this is the one we are gonna use right here. So this is a 0, again because the ball is rolling initially on a flat table, so it's all horizontal action. So as you can see, your final velocity before it strikes the ground depends on A of y multiplied t. Let's compute that very quickly. And the time. So this velocity, y component, before it strikes the ground is 383 meter per second, frame it. At this point, I'm going to compute the magnitude of V, as the square root. You remember v of x square plus v of y square. V of x, you have it. V of y, we just found it. And this one will come out, did I do the math? I think, yeah, 524 meter per second. And the direction is the inverse of the tangent of absolute value, vertical over horizontal. So when you plug in, you will obtain an angle of 46.9 degrees, which is located below the x-axis, below the horizontal. So what does it mean? This is the table. The ball is rolling with an initial velocity only on the x-axis. It's flat. It falls, strikes. So you have v of x, that is 528. You see v of x right here? 528, like that, 528. This is v of x final. V of y is pointing downward at 383 meter per second. I'm going to do the parallelogram, and the final V in green will be the diagonal. This is V, the final. The angle is this one, counterclockwise down from the x-axis, 46.9. Now you may be wondering, what if we didn't flip the axis? What if we kept the same convention? What? Well, nothing would have changed, absolutely nothing. Because with this convention here, with this negative sign, I'm going to show you what will happen, okay? Now, I'm going to use in blue the negative sign. If I would have kept, you will have a displacement here that has to be negative, and the downward acceleration also negative. Nothing would have changed. For the horizontal, nothing would have changed. And here, what would have changed is that you would have had a negative sign, which would have gave you a negative sign, which would have tell you that the final velocity y component points down. Here, nothing would have changed, and nothing would have changed. So as you can see, if I don't flip, if I keep the standard Cartesian, I have to carry all these negative sign with me, which is okay. Or you can flip it like I did, so all those quantities are positive, so it's a little bit easier. UCM is actually an easy concept, uniform circular motion. But take a look, there is a pilot blackout in a power drive. So this jet plane comes in for a downward dive. The bottom part of this path is a quarter circle, all right? Quarter circle, so this is a circle, which allow us to experiment with UCM. According to medical tests, pilot lose consciousness, very dangerous, at an acceleration of 5.5 times the acceleration of gravity. We want to find the speed in meter per second and miles per hour. Actually, I like to write it miles over hour. It's a little bit better. You know, this is the speed that the pilot will experience when she loses consciousness, he or she loses consciousness. So let's do this one. First, this is a circle, right? So there is a center right there. So there is an acceleration that is radial, which is also centripetal, right? Along the radius or pointing toward the center, that is A of C. A of C, remember, was given by how fast is it moving divided the radius of curvature. This radius is given by the problem right here, 350. So we want to find V, right? So V can come out from this equation right away. All right, let's do that. Let's start first theoretically. So this speed of this pilot will be r that multiply your acceleration, which is given by the problem. Let's plug in the radius of curvature. Now the acceleration is a 5.5 times g, which is, remember, a value of 9.80 meter over a second square. Now, if you do the math under the square root, you will obtain 140 meter per second, which correspond at 310 miles per hour. Unbelievable. Both final and